If you were to ask who the most important scientists in history are, especially in the field of physics, who are the figures who have ushered in and ushered out eras in history? Which names come to mind? Of course, if you ask die-hard science enthusiasts, they'll rattle off a whole list of names. Of course, they'd surprise everyone with their answers. They'd immediately mention Max Planck, Niels Bohr, Heisenberg, Schrödinger, Max Born, Volta, Ørsted, Bell, and many others. But if we were to stop just anyone on the street, if we asked someone who's taken a physics class in school, the first names you'll hear will be Isaac Newton and Albert Einstein. A third one? I don't know. You'd have to really push it. Yet there is a third great scientist, one who has remained hidden between the lines in books, known by very few, and whose true worth is rarely acknowledged by those who do know him. A figure no less significant than Newton and Einstein, and perhaps even the very person who made Einstein into Einstein. A name he admired so much, he hung his photo on the wall of his office. James Clerk Maxwell. Do you know what Einstein said about Maxwell? While discussing the theory of special relativity, which changed everything, the starting point of the theory of special relativity is Maxwell's equations of the electromagnetic field. And he added this: since Maxwell, physical reality has been expressed through interrelated fields. This shift in the perception of reality is the most revolutionary insight since Newton. There's more. Ivan Tolstoy, who wrote Maxwell's biography, said the following about Maxwell. Maxwell's influence on the history of science is as great as that of Einstein, who was inspired by him, and even as great as that of Newton, whose discoveries he, in a sense, overshadowed. But that's not all. Professor R.V. Jones had this to say about Maxwell's paper on the theory of the electromagnetic field presented to the Royal Society. This research is the first evidence demonstrating the existence of radiation alongside light and heat, and it is one of the greatest strides ever taken in human history. In addition, Max Planck, the man who ignited the spark of quantum physics, said of Maxwell, he accomplished feats unprecedented in history. And finally, Richard Feynman, widely regarded as history's greatest teacher, whom I've personally prepared a special video about, said of Maxwell, when I think about humanity's future, say 10,000 years from now, there is no doubt that when people look back at history, they will view Maxwell's discovery of the laws of electrodynamics as the most significant event of the 19th century. Aren't these very important references? Yet for some reason, Maxwell is rarely mentioned and his contributions are seldom acknowledged. I'm not entirely sure why, but while reading about him, I came across a passage where he said, the reason historians mention Maxwell so little is likely because they haven't understood what he achieved. They overlook him because they don't understand. Well, a man about whom so many praises have been sung must be quite extraordinary, isn't he? What did he do, and what did he change to deserve all these accolades? Let's give Maxwell his due, because his story, like Faraday's, has a lot to teach us. The reason I made a video about Faraday beforehand is that Maxwell's story, in a way, picks up where Faraday left off and builds upon it. And here's an interesting fact for you. When Faraday first presented his findings on electricity and magnetism, the year was 1931, the year Maxwell was born. Maxwell, however, passed away in 1879, and in the same year, Albert Einstein was born. Of course, it's symbolic and doesn't mean anything in itself, but since we see this continuity and consistency in the theories of these three men, I believe it's a very nice coincidence. Maxwell had already published a paper on geometry by the time he was just 14 years old. He tried to explain everything he saw and all the questions in his mind through mathematics, and he was quite successful at it. By the time he began his studies at the University of Cambridge at age 19, he had 3 published works to his name, and by his early 20s, everyone would begin to hear his name. You know Saturn's rings. They're one of the most extraordinary and striking formations in our solar system. Yet for centuries, no one knew what they were. Everyone had a theory. Some said these rings were liquid, others claimed they were a solid rock formation. In 1857, a contest was organized to solve this mystery. A prize was offered for anyone who could explain these rings. Here, Maxwell steps in again. He expressed through an incredible mathematical formula that this formation could only be caused by the gravitational motion of millions of tiny particles. See, this is what I mean when I say mathematics. Saying that Saturn's rings are made of particles is one thing, being able to express their movements with numerical values through a formula is another. This was the quality that set Maxwell apart, and he would be the only person to submit a paper for this competition. Following this success, Maxwell would begin to gain a certain level of popularity. Many people were saying he was one of England's best theoretical physicists. Unsurprisingly, he would earn the title of professor at the University of Aberdeen at the age of just 25. But before that, we'd witness him turn another obsession into yet another amazing discovery. You'll notice we haven't gotten to electromagnetism yet. That's the really important part. But look at what else Maxwell gave us. Another subject that Maxwell, who was completely consumed by his curiosity in every sense, couldn't get out of his head was colors. In our video on colors, we discussed how Newton had discovered where colors came from, but Newton couldn't explain how colors mixed or how different colors emerged, and for 150 years, hardly anyone had given this topic much thought. Only Thomas Young had a theory. He believed biology played a key role. He proposed the theory that there are receptors in the human eye corresponding to the primary colors used by artists. This was an amazing discovery, but the task of providing the necessary explanation and formulating it would fall to our mathematical genius, Maxwell. Using a very simple setup, the color wheel, he would first test this on his friends. He would discover that a rapidly rotating color wheel tricks the human eye into perceiving colors that arise from the mixture of existing colors. Later, he would develop a mathematical formula that tells us which color we can obtain by mixing the three primary colors in what proportions. In other words, he was the first person to write the mathematical formulas for the color scales and color codes we use in programs like Photoshop. He didn't stop there. Do you know what he did next, building on that theory? He was also the first person in history to take a color photograph. Here is that photograph. He projected it onto the wall from a projector right in the middle of a lecture on color at the Royal Institution in 1961, while explaining what the primary colors of light are and how colors are mixtures of them. And for the people in that room, it was nothing short of magic. For us, it was actually the beginning of everything. The red, green, blue color system he introduced was the very principle underlying any device you're watching this video on right now. The origin of RGB, at the time, he was just 29 years old, and he would go on to become one of the youngest scientists ever admitted to the Royal Institution. However, when Marshall University, where he had become a professor at the age of 25, merged with the University of Aberdeen, an older professor with more seniority would take his place, and James Clerk Maxwell would find himself unemployed. Yes. On top of that, he hadn't had an easy childhood. He was the only child in his family and had lost his mother when he was just 8 years old. He would also lose his father a few months before becoming a professor. Maxwell, who had a very emotional personality, even writing poetry and possessing an artistic side, began to feel quite lonely. During this time, he met Catherine, who would support him in all his work, and they married after he proposed to her with a poem. While he was unable to work, Maxwell also managed to farm. After being rejected by several universities, he began working at King's College in London. This marked the beginning of a period when he would accelerate his work on electricity and magnetism. He had been interested in electricity since childhood and had been conducting his own experiments on the subject. Moreover, humanity had already encountered electricity long before. Lightning, in particular, captivated everyone's imagination. Figures like Benjamin Franklin, whose portrait we see on the dollar bill today, and who would later become one of America's founding fathers, were experimenting with kites to capture electricity. We were already actively using magnetism. Ships found their way using compasses that relied on the Earth's magnetic field. But as we mentioned earlier, very few people would recognize the connection between these two forces until Faraday came along. Remember, Faraday made tremendous contributions to the fields of electricity and magnetism and opened a very important door. He discovered that electricity generates a magnetic field and that a magnetic field generates an electric current. He was the first person to show these two forces as a unified whole, but he wasn't entirely sure what all this meant, nor could he express it mathematically. He didn't possess that ability. This is where Maxwell would come into the picture. He believed that a mathematical explanation was needed to demonstrate the relationship between electricity and magnetism, and he would dedicate all his time to uncovering it while working at King's College. He simply believed in Faraday. And after a very long time, he would write down 4 formulas, which we now call Maxwell's equations, that would change the world. These formulas, they were later simplified and written as follows. Just looking at them gives you a headache, doesn't it? But as you know, we never had to deal with the formulas themselves. Let's talk about what these formulas are telling us. Once we understand what they mean, the equations begin to make sense to us. The first one, Maxwell's first equation, is also known as Gauss's law, and in short, it states the following. It explains how a static electric charge generates an electric current. The second equation is also known as Gauss's law for magnetic fields, and in short, states the following. Magnetic poles always exist in pairs, and the magnetic charge is always zero. You're probably familiar with the third equation, Faraday's law, as it's also called. It states that a change in the magnetic field generates an electric field. The fourth and final equation is known as Ampere-Maxwell's law, and it states that, for example, an electric current flowing through a wire creates a magnetic field. But the truly striking discovery would emerge when he brought these equations together. When he tried to combine these formulas, each of which worked perfectly on its own, he would realize something was missing. To address this, he would make an addition to the final equation after its initial form. And with this addition, the fourth equation would demonstrate, as we mentioned earlier, that a change in the electric field creates a magnetic field. In other words, he had managed to distill everything we've discussed into a few formulas and explain these hidden laws of the universe with just a few expressions through mathematical magic. How a change in one affects the other, and a change in the other affects the first. Like mirrors, how these two forces are inseparable. Electromagnetism. He had managed to explain it all. With this, he had risen to the very pinnacle of the scientific world. He had become the most renowned, most important, and groundbreaking theoretical physicist of his time. But Maxwell couldn't sit still because of his innate curiosity. He would immediately set out to explain another phenomenon that Faraday had intellectually proposed using these equations. In the Faraday video, we briefly mentioned his theory about light and how everyone had mocked it. In this theory, Faraday had claimed that light was a kind of vibration in lines of force, and he even went further, suggesting that these lines of force were the force holding particles and the mass of matter together. Nonsense, everyone had said, of course. An invisible force line? Like an electrical cable, then? Faraday had a mental image of this. He believed that the vibrations occurring along a line among particles connected by these force lines were transmitted to one another in the form of a kind of wave. The very fact that he was able to conceive these ideas without any evidence proves once again what a genius we are talking about. However, as I said, he couldn't express this, and Maxwell was one of those who said, well, that makes perfect sense. He would combine this incredible idea with his pure and unique mathematical genius. Along with the equations we mentioned earlier, Maxwell was also explaining that electromagnetic waves travel through a vacuum, and he set out to calculate just how fast this movement through the vacuum was transmitted. This is where his magic comes into play. When he looked at all the formulas and calculated them together, he saw something no one else could see: the connection that Faraday had predicted but couldn't see himself. When he divided the electric constant by the magnetic constant, the result was the square of a speed. But what kind of speed was this? Which speed? Where did it come from? Yes, the result that emerged, it was approximately 300,000 kilometers per second. In other words, it was the speed of light. The speed of light had been calculated before, but what did it mean for this exact speed to emerge in these equations? It meant that Faraday was right, that light is an electromagnetic wave. It told us what light is. This was a very, very important discovery, one that shook Newton's laws to their core, changed them, and developed them, that we needed to recalculate many things. A simple yet crucial discovery that would help us understand how the universe works, and at the same time, it would present the phenomenon we call the electromagnetic wave to the scientific community and to us as a gift. It would change the world. However, here, Maxwell would face the exact opposite of the problem Faraday had encountered. He had predicted these waves in his equations and expressed them mathematically with clarity. But just as Faraday could not experimentally prove his equations, Maxwell could not experimentally prove his equations. And once again, fate would chart a similar course for him. When he began speaking of invisible waves whose theories remained unproven, the scientific community would begin to view him with skepticism as well. And 20 years later, when a German scientist named Heinrich Hertz physically proved the existence of these electromagnetic waves, everyone would realize he was right. Of course, everyone here had asked the same question. So what? I mean, great, you found them, but what's the point of these electromagnetic waves? Hertz himself had said nothing. They're just proving Maxwell was right. How wrong he had been, though, because what Hertz discovered were radio waves, and look at what these waves changed. Shortly after, Marconi invented the radio, and then television entered our lives. Later, radar was invented using higher frequency radio waves, from airplanes to ships, all the way to military applications. Then came microwaves. As the name suggests, we use them in the kitchen. But more importantly, these microwaves made mobile communication possible. Then came infrared waves. In thermal imaging, they began to be used in remote controls. Ultraviolet waves were discovered later. They were going to be used in fluorescent lamps in medical research. Then came X-rays, the rays we use in cancer treatment or for sterilizing food. If we were to go into detail about each one, these discoveries and inventions which have transformed our lives in every way are based on a few equations Maxwell published some 150 years ago. Perhaps this is why in the late 19th century people approached them with skepticism, or why even today many people don't even know his name. Maxwell was talking about invisible, intangible things, and he would never see what they led to. You might think that after these revolutionary works, Maxwell returned to his father's farm to enjoy his retirement. But no, he would go on to conduct research on thermodynamics, which we'll discuss in detail later. After spending a long time conducting his own research on the farm, Cambridge would invite him and he would set up a laboratory for himself there, that famous Cavendish laboratory. It was in this laboratory that the electron and the neutron would later be discovered. In 1953, the structure of DNA would be visualized for the first time using X-rays. The research conducted here would yield 29 Nobel Prizes. But Maxwell, who later returned home, would die at the age of 48, the same age his mother had been when she passed away from the same disease, stomach cancer. Incredible achievements packed into such a short life. I hope I've managed to explain why Maxwell is so important and to what extent he has influenced our lives, even though there are many other works we haven't even mentioned. The technical implications are, of course, extremely important, but I believe what's truly significant is that he sparked an irreversible shift in the scientific community's perspective of the universe. We would begin to look at the universe underlying the world we can touch and see. I'm sure you can understand what I'm trying to do with this series. On this journey from classical physics to quantum physics and beyond, I'm striving to tell a comprehensive story that everyone can benefit from by focusing on what things actually are rather than just formulas and equations. I hope the series will continue in this way, moving forward or backward in time as needed, and that when it's finished, it will serve as a comprehensive physics guide. Perhaps it might inspire some of us, motivate us, or prompt us to ask the right questions. Perhaps some of us might change the world for the better. And as always, until we meet again, thank you for being here. Best regards.